So today I'll be talking about XRD and SEM applications in corrosion testing. The topics I want to discuss, first an overview of corrosion testing, what it is, how it works, what it's for, and then I will be reviewing a study done on the characterization of corrosion products on carbon steel exposed to natural weathering and to accelerated corrosion tests. So the study was aiming to figure out how well these two test parameters are correlated, the test parameters being the natural weathering versus the accelerated corrosion test done in a lab. And then I'll be discussing some analysis that I did at Modine Manufacturing. These were done on tin-plated copper hairpins. And I'll just be discussing some of the SEM analysis that we did. So this is just a simple kind of schematic of your typical QFOG salt chamber. So this is what we use for corrosion testing. As you can see on the right, you place your samples on the inside, and there's a control panel on the right there. You can regulate pressure, temperature. You can sometimes even set up what type of ASTM method that you want to use. And then on the left, you can see in the middle there's the spray tower. This is connected to an atomizer, which creates a fog or a mist of our salt solution, which is collected onto your test specimens. And generally, we'll keep these in there for about anywhere from 500 to 2,000 hours. The major phases that we see from steel samples are the lepidochrosite, goethite, magnetite, and cagnite. So these are iron oxide hydroxides. The magnetite's an iron oxide. The cagnite is sometimes referred to as the beta phase of these first two phases, and that phase is mostly seen due to the chloride content of the sodium chloride test solution. So just jumping right into the review of this article done on natural weathering versus accelerated corrosion testing. I'll just review the test parameters. So carbon steel was used for their test specimens. They use 15 centimeter panels for all of these tests. And the first two locations, test locations, are located in Brazil. So our natural weathering 1 parameter, this is our urban or polluted location. And the specimens were exposed for 9 months. And I do just have the ASTM method listed there for reference. For our natural weathering 2 parameter, this is considered the industrial location. Again, a 9-month exposure, and the same method was used. For our lab test, accelerated test A, we have our prehesion cycle. So this is an ammonium phosphate and sodium chloride mixture, and the test specimens were cycled in and out of that cabinet, and also a UV radiation and condensation cabinet for a total of 4 cycles. And accelerated test B, ASTM B117 was used. This is just a fog cabinet with a sodium chloride test solution, and these were cycled in and out of the UV radiation cabinet as well for a total of 4 cycles. So the XRD analysis parameters, copper Ka radiation, 40 kilovolts, and I also have the PDF database that was used on the bottom there. So these are the XRD results for the natural weathering parameters. Site 1, again, was the polluted environment, and the major phases that we're seeing are the lepidochrosite and the goethite. Site 2, our industrial environment, we are seeing lepidochrosite and goethite. And then if you look at the 6-month marker, we're starting to see magnetite, and even more so after 9 months in test site 2. So these are our micros from our natural weathering parameters. We're seeing these cotton ball-like structures, and also the nest formations. So these are typical of semicrystalline goethite. Our 3-month photo on the bottom there is from site 2, and we're seeing sandy crystals of lepidochrosite, which is the main phase in our natural weathering. So here we have our XRD results from our accelerated testing. You can see the major phases are goethite and magnetite. In test B, which is the sodium chloride UV parameter, we're also seeing a caganite. If you look on the bottom left, you can see there's just a small amount, and again, this is due to the chloride concentration from our 5% sodium chloride test solution. And our micrographs from our SEM analysis for the accelerated test, you can see they're a lot different from the natural weathering micros. What we're seeing is much more crystalline, regular, sharp structures. And we got a micro of the magnetite, which we did not have with our natural weathering parameter. And here's just a side-by-side of the micros, just so you can really see the difference between the goethite and the lepidochrosite. Again, with the natural weathering, we're getting these sandy lepidochrosite structures, and then the cotton ball structures for the goethite, which are interconnected with those nest formations. And then with the accelerated tests, we're getting these much more crystalline looking images that are typical of a more aggressive test. So just a side-by-side of the XRD analysis as well. You can see the natural weathering sites 1 and 2 have main phases of the lepidochrosite and the goethite, where we're seeing major phases of goethite and magnetite with our accelerated testing, and really not much lepidochrosite at all. And then again, we do have the caganite on that test parameter B. So why was magnetite observed after 6 months of exposure in test site 2, but not observed in test site 1? Well, magnetite is the final form of iron oxide during atmospheric exposure of carbon steel, so it would be favored in a more aggressive environment. If we look at the corrosion rates of these two locations, we can see that test site 2 has a much higher corrosion rate when compared to test site 1. Why was magnetite shown in the site 2 XRD analysis, but not in the SEM micrographs? The formation of magnetite can begin on the inside of the rust layer because it favors low oxygen environments. So this is why we can see it in an XRD analysis, but it's not always going to be visible just from the micros that we get on an SEM. Why was more goethite observed in site 1 samples? Well, higher goethite levels are due to the SO2 contamination. So again, this is our more polluted test site. So goethite's going to be favored there just due to the pollution, the SO2 contamination. So just in summary, a comparison of the two, we're seeing very different phases from our natural weathering versus our lab test. And we're also seeing in the crystal structures, you know, in a natural case, you're not going to see very crystalline images. It's going to be more of the cotton ball type structures or the sandy crystals. Whereas in an accelerated test, you will see very regular, sharp crystals. And again, we'll also see the acagonite if we're using a high concentration of sodium chloride. So what we've learned is really natural weathering and accelerated lab corrosion testing is not very well correlated. However, this is an industry standard, especially the ASTM B117, which is just the 5% sodium chloride test solution. And so most companies will continue to use these type of tests to validate suppliers and just to compare to old test results, just because there's a large history of old results to compare to. And here I just have the reference of that study. So now I'll be going over a little bit of some analysis I've done at Modine. So these tin plated copper hairpins are used in refrigeration units. Again, we use ASTM B117, and this was tested for 500 hours in the salt spray chamber in the picture on the left there. So after a corrosion test, you can't always see macroscopically whether or not it's corroded through. So we have we cut up some of these samples post-test and put them on the SEM. We have our selected areas here. Selected area 1, we're just expecting that to be our kind of baseline. We are going to see mostly just tin still on there. Selected area 2 is inside of a corrosion pit. This is the area that will tell us whether or not this test has failed, whether or not we'll see copper. And then selected area 3 is in what looks like a corrosion pit. So we would expect to see a little bit of copper there as well if this tube is failing the corrosion test. So our selected area 1, we're seeing it's mostly tin and very small amount of copper, not enough to constitute a failure. And on the left side there, you can see all the chlorides that's just left over from the sodium chloride salt solution. Selected area 2, again, it's mostly tin. We have the chlorides, and then on the far right, we can see that where we have these peaks that correspond to more copper, and this is kind of expected. It's right in the middle of a corrosion pit, and this would be enough to constitute a failure for this test. And then our selected area 3, this is the spot where we weren't sure if it was a corrosion pit or just kind of a weird spot. And there's a little bit of copper there, but again, our selected area 2 is really our failure mode there. Another tube with a different supplier. So we have our selected area 1, that's our baseline of what we would assume wouldn't be failing. Selected area 2, again, more of a baseline, but it's closer to a pit, so we might see some copper coming through. And then area 3, right in the middle of a corrosion pit. That's where we'll be expecting to see copper if this is failing. So again, not much different than the first supplier. We have our tin, we have our chlorides, not enough copper to constitute a failure on this first selected area. Area 2, again, not enough copper to constitute a failure. And then in area 3, we can start seeing our peaks of copper, and so this corrosion test will be considered a failure for the supplier as well. Okay, and that's all I have today. I hope you enjoyed. If you want to ask any questions, I will do my best to answer them, and thank you for watching.